IL-11 for short, is a gene in our body which creates a protein that functions to activate fibroblasts and also immune cells. And this is something that we've inherited in an evolution actually from fish, and it does good things in the fish. Unfortunately for us, it's an evolutionary hangover. It causes harm and it causes disease. It causes inflammation, fibrosis, and unfortunately stops our tissues from regenerating properly. What we found back in 2016, 2017 was that people had mischaracterized it. And so we were the first to describe this gene as a pro-fibrotic, pro-inflammatory factor in the heart and kidney, and went on to show that it did this in multiple tissues. And from that, our new study into aging developed. So the segue from what we were studying, which was fibrosis, tissue scarring, to aging, we just happened to do an experiment and we just suddenly noticed that our favorite gene that we were studying already was really high in an old animal. And so we studied it across ages in mice. And lo and behold, this gene, which we know does bad things, is going up in all tissues in the mouse with age. And so that opened the question that we knew it was a bad gene. When it gets turned on, it causes trouble, what we call multimorbidity. Multimorbidity is diseases of aging across your whole body. And these range from your eyesight, to your hearing, to your loss of hair, to losing muscle, to your pump function of your heart, to your kidneys functioning. So the question was, in the mouse, is it somehow contributing towards aging? And this premise was not just based on the fact it was going up, it's based on the fact that we know that IL-11 does activate specific switches. And so what we did in a mouse is we were able to manipulate the genome and turn the gene off. And what we see is if you take away the IL-11 gene in the genome, aging diseases are much improved. We then moved on to a more translationally relevant approach, which is an antibody. And what antibodies do is they will bind to a substance, in this case IL-11, and mop it up. So we took our mice when they're about human equivalent 55 years old, which is 75 weeks in a mouse, and we gave the injection and we said, what happens? It does the same thing. The mice had stronger muscles, they had better lungs, they had better skin, they had better hearing, they had better vision. So they had multiple improvements by a therapeutic intervention. So not only can we do it by deleting the gene from birth, but we can do it with a therapeutic, a drug given late in life, which opens up this possibility of now taking this to humans.
The interest of my group is working on senescence, and we are interested on that because senescence underlies cancer, aging, and many related diseases. And not only that, but that we also see that there are a correlation or there are other benefits that we can just measure in other of the hallmarks of aging. So somehow we can learn also of how these mechanisms are interrelated, and that can help us to design better synergistic treatments in the future.
One of the most important things, I think, and discriminators that we have in what we've done here is we've shown that with a single reagent, anti-IL-11 therapy and antibody, we can improve health span and lifespan. The target population for anti-IL-11 therapy is the world, but much prior to that, we've have to get through testing efficacy in human trials, which are difficult to fund and have regulatory issues. But yes, I do see strong translational potential. The genetic data, all the data from the animal studies all points to a promising safety profile.